Welcome back. Today we're diving deep into a programming language that, well, it tries to do two things at once, really. Serving Python's simplicity, but also tackling complex relationships in data. We're talking about Jack.
That's right. Jack is pretty interesting because it sets itself up as a native superset of Python.
Hmm.
Our sources really dig into this kind of ambitious goal. You get the familiar stuff, standard computing,
Uh-huh.
but also this, well, revolutionary framework for managing connections. So our mission today is to get a handle on that mix, especially what Jack calls object spatial programming, or OSP.
Okay, let's start where it feels comfortable, the Python side. If you, listening, know Python, you're basically, what, 90% there for the basics, standard variables?
Yeah, exactly. Your stray, int, float, bool, they all work just like you'd expect. No surprises there.
And the core logic flow.
Preserved. Your if, elif, else, loops, it's all that readable logical structure Python developers know.
Yeah.
And for simple things, isolated data, you use object classes.
J classes, what's the difference there?
They're like enhanced Python classes. You declare attributes using the has keyword, and they support standard object-oriented inherits. Think Python, just maybe a bit more explicit.
Got it. So familiar ground, mostly. But, okay, this is where it starts to feel different, right? The friction starts. Jack seems built for something else.
It is. While it keeps that Python readability, and this is key, it completely ditches indentation for code blocks.
Whoa, okay. No Pythonic whitespace.
None. Whitespace doesn't matter for execution order. Instead, Jack uses curly braces, like C, Java, JavaScript,
Yeah.
a lot of languages.
That's going to mess with some muscle memory for sure. But I guess it signals a move towards being really explicit about structure. No ambiguity.
Exactly, which becomes super important when you're dealing with these complex graph structures we'll get into. Also small things, but important.
Yeah.
There's a standard entry point with entry,
Okay.
and every single instruction needs a semicolon accent at the end.
Right. Like C-style languages again.
So, yeah, the initial takeaway is Jack blends Python's nice high-level feel and type clarity, but it enforces the structural discipline of languages that are maybe more serious about compilation and optimization.
You get faster execution, maybe? Clearer boundary.
That's the idea. And you need those clear boundaries when your computation starts, well, moving around.
Okay, so why? Why invent this dual thing? Couldn't we just use a really good Python graph library? What's the actual problem Jack is trying to solve?
It boils down to how traditional OOP, standard object-oriented programming, handles relationships. And honestly, it doesn't handle them very well.
How so?
Think about modeling something connected, like prerequisites for tasks, or even just a social network. Alice is a person object, Bob is a person object. They become friends.
Okay, so Alice's object gets an attribute, like has friends, like list, and you add Bob to the list.
Right, but here's the catch. For it to be a mutual friendship, you have to manually write code to update both objects. You add Bob to Alice's list.
And then you have to remember to add Alice to Bob's list, too.
Exactly. You have to write that boilerplate code yourself. You call Alice's method, and inside that, you better remember to call Bob's method too.
Okay, but is that really such a big deal? It's just a couple of lines of code, isn't it?
It's not about the lines of code. It's about the architecture. It's a failure of separation, really. When data gets highly connected, this way of doing things is, one, verbose, lots of repetitive code.
Okay.
Two, it's super error-prone. Forget that second update, and your data's inconsistent.
Right, suddenly Alice is friends with Bob, but Bob isn't friends with Alice. Oops.
Exactly.
Yeah.
And maybe most importantly, it treats the relationship, the friendship itself, like it's just a passive piece of data stuck inside Alice or Bob. It's not treated as its own thing, with its own potential properties or behavior.
So you're constantly doing this manual linking, double-checking consistency. It sounds pretty rigid, especially for the complex stuff we see now, like knowledge graphs, supply chains, family trees.
Precisely. It just doesn't scale well, conceptually. Jack's approach says, if you're modeling relationships, the native structure should be a graph. So Jack makes graph elements first-class citizens in the language.
You mean like int or strile?
Kind of, yeah.
Yeah.
You have nodes. These are your data locations, the people, cities, tasks.
Yeah.
And you have edges. These are the connections, the relationships, the friendships, roads, dependencies. They're built-in concepts.
So not a library you import, but fundamental types baked right into the language and compiler. They are the architecture.
You got it. That's the foundation.
Which leads us, I guess, to the really unique part. Object spatial programming, OSP. You said it's the difference between writing code about a graph and writing code that lives inside it.
Yeah, that's the core paradigm shift. Think about traditional OOP again. If I want to calculate something involving Alice, I call a method on Alice's object. The data, Alice, stays put, and the computation comes to the data.
Standard procedure.
Right. But OSP flips that completely. The data, the nodes, they're arranged in this graph space. They stay put. But instead of calling a method on them, you create this mobile unit of code, a walker.
Walker.
Yeah, a piece of code that can move. You send this walker out to travel through the graph, node by node, edge by edge.
Okay, hang on. So the analogy you used earlier, traditional OOP is like ordering pizza delivery to your house.
Right. Computation comes to the data.
But OSP is like sending a little robot out.
Exactly. A little robot, the walker, that goes out on a mission. It visits different restaurants, the nodes, maybe collects ingredients, performs actions at each stop based on its instructions.
That's a very different way of thinking about computation.
It really is.
Right.
And that ability, sending computation that holds its own state and moves across relationships, that's the Jack magic. It tackles graph traversal optimization inherently because the computation lives along the structure.
Okay, so that clarifies the three main OSP building blocks you mentioned. We have node.
The data holder, the place in the graph.
We have edge.
The connection itself, defining the relationship between nodes.
And walker.
The mobile code, the robot, the thing that travels.
And you said edges can hold their own data, too.
Absolutely, because they're first-class objects. So you could have, say, edge, friendship as since, int. The connection itself knows when the friendship started.
So the relationship isn't just a pointer, it's an object with its own attributes. That's powerful.
It makes the relationship itself something you can query and track, separate from the nodes it connects.
And making these connections sounds much simpler than that manual list updating.
Way simpler. It's declarative. If Alice connects to Bob, you just write Alice plus Bob. That creates a directed edge.
Plus for forward connection.
Yep. And if it's mutual, like a friendship, you use the bidirectional operator. Alice plus Bob.
Plus Bob, got it.
And it's crucial to understand, these operators aren't just fancy syntax for list updates. They are telling the compiler to build and manage the graph structure. It's foundational. That relationship object is created, managed, and ready for a walker to traverse immediately.
Right, so we've built the map, the static structure of nodes and edges. How does the walker, our robot, actually move through this space? How does the computation travel?
Walkers run functions called abilities. Think of them like methods, but they're often triggered automatically by events during the traversal.
Events like?
Well, every journey needs a start. So a walker usually has a can start with root entry ability. That's where it kicks off, typically at a specific starting node.
And then when it arrives at a node it cares about.
It executes a beat ability. And this is cool. It's type-driven. So if you define can meet person with person entry, that ability automatically runs whenever that specific walker lands on any node defined as a person.
So the walker says, I'm interested in people, and when it finds one, the meet person code runs.
Precisely. That's where the interaction happens. The node influences the walker can read or modify the node.
You used the term type-driven interaction earlier. Can you break that down a bit more? Sounds a bit jargony.
Sure, it just means both sides get a say in what happens. The walker, the traveler, says, I'm looking for nodes of type X. The node, the destination, can define its own logic saying, if any walker lands here, this is how I react. Or even, if a walker of type Y lands here, do this specific thing.
Okay, so it's a two-way street defined by the types involved.
Exactly. It allows for really clean separation. The walker knows its job. The node knows how to respond to visitors. It's quite elegant.
And inside the walker's code, how does it know where it is or manage its own data?
There are special references. Here always refers to the node the walker is currently visiting.
Okay, here is the current location.
Self refers to the walker object itself. That's where the walker keeps its own state, maybe a list of nodes visited, a running total, whatever its mission requires.
Self is the walker. Makes sense.
And then there's visitor. This one is used inside a node's ability if the node needs to refer back to the specific walker that just landed on it.
Got it. Here, self, visitor. Now the key thing.
Right.
How does it move? What makes it go from one node to the next?
That's the visit statement. It's super simple but powerful. If a walker is at, say, node A, and you write visit inside its ability.
Visit with the arrow.
Yeah, that tells the walker, okay, look at all the outgoing edges connected to here, node A, and automatically move along each of them. For each edge it follows, it will land on the next node and trigger the appropriate mutability there.
So one visit statement could potentially trigger multiple moves and subsequent ability calls.
Absolutely. It handles the fan out automatically. It replaces all that manual looping and recursion you'd normally write to explore neighbors in a graph.
That sounds incredibly concise. Now, what about getting results back? If the walker is collecting data, how does it report back without just stopping? You mentioned report versus return.
Right. Standard return works like in any function. It sends a single value back, and boom, the function execution stops. The walker's journey ends right there.
Okay.
But report is different. It's designed for streaming results during traversal. When a walker executes reports some value, that value gets sent back to whoever started the walker.
But the walker keeps going.
Exactly. It finishes its current ability, processes the visit statement, if there is one, and continues its journey through the graph. It keeps reporting back values as it finds them.
Ah, so if a walker is visiting all person nodes to collect their ages, it would report age at each one, and the caller would get a stream of ages.
Precisely. Perfect for aggregation, finding all matches, any task where you need multiple results from across the graph structure without stopping the exploration.
Okay, that report mechanism sounds useful, but you also mentioned asking questions without needing a walker to traverse everything. Declarative querying. The example you gave looked dense.
Yeah, it can look a bit symbol-heavy at first, but it's incredibly powerful once you decode it. This is where OSP lets you query the graph structure directly. Let's break down that example again. Old friends is Alice. Friend since 2018-80.
Okay, walk me through it means.
The square brackets signal a declarative graph query. Think of it like a mini language for path description.
Starting point is Alice.
Yep. Then Alice means follow an outgoing edge.
Simple enough.
The first colon introduces an edge type filter. So friend means only follow outgoing edges that are specifically of type friend. Ignore other edge types like coworker or whatever.
Okay, filtering the edge type. Then another colon.
The second colon introduces a filter on the edge's data. Remember, edges can have attributes, so since 2018 checks the since attribute on the friend edge itself.
Ah, filtering the edges based on their own properties? Clever.
And finally, the last daf says what you want to select at the end of that filtered path. In this case, it means select the node connected by that valid edge.
So putting it all together, start at Alice, follow outgoing edges, only consider friend edges, only keep those where the since attribute is less than 2018, and give me the node at the other end of those edges.
You got it, in one line.
Okay, I see the power now. Compared to writing loops, checking types, checking attributes inside the loop in standard Python.
Yeah.
That's dramatically cleaner.
It really is. It lets you express complex graph queries very concisely.
Let's make this concrete. The task manager example you brought up, tracking dependencies. Classic graph problem, right? Task A needs task B and C, task B needs D.
Exactly, a perfect fit for OSP. You can't start a task until its prerequisites are done.
So how would you model this in Jack? Define the structure first.
Right. You define a node task, probably with a has status, stresser, attribute, maybe pending, ready, complete.
Okay.
And then you define an edge dependent to represent that prerequisite link. If task A depends on task B, you'd have an edge B depends on A.
Makes sense. So the edge points from the prerequisite to the task that depends on it?
Usually, yeah. Now the goal is task A ready to start? Meaning, are all tasks it depends on, like B, complete?
So we need a walker.
Yep. Let's call it walker check ready.
And where does it start? At task A.
It would likely start at the task we're interested in, say task A. Its job is to check if A is blocked by any incomplete dependencies.
So it needs to look backwards along those depends on edges.
Correct. Its ability maybe can check deps, would run a task A. Inside that ability, it needs to examine the incoming depends on edges.
And it could use that declarative query syntax.
Absolutely. It could do something like unmet deps here, or depends on a dep.status, complete.
Whoa, okay, break that down. Here is task A means follow incoming edges.
Right. Then Bemin filters for only dependency edges.
Them dep.status, complete. How does dep work there?
Good catch. The query syntax often lets you assign a temporary variable, maybe implicitly or explicitly, to the node being checked at the other end of the edge during the filter. So dep would refer to the prerequisite task, like task B. We check its status.
Okay, so check the status of the node at the start of the incoming depends on edge. And the final means select that prerequisite node if its status is not complete.
Exactly. So that one line finds all immediate prerequisites of here, task A, that are not yet complete.
And if that unmet deps list is empty,
then task A is ready. If it's not empty, task A is blocked.
But what about nested dependencies? If task A needs B and B needs C, does the walker handle that?
This is where visit comes back in, but maybe used differently. The check-ready walker, when it finds an incomplete prerequisite, say B, might need to visit that node, B, to recursively check its dependencies, or it might just report blocked immediately. The exact logic depends on the goal. But the key is that the walker can traverse recursively using visit.
So the walker automatically handles navigating that dependency chain, however deep it goes.
Yes, combined with the declarative queries, it lets you separate the dependency structure defined by nodes and edges from the how, the logic of checking readiness defined in the walker. It's that separation of concerns again.
Okay, wrapping this up then. This deep dive really highlights that Jack isn't just, Python with funny braces. Learning it means getting your head around two paradigms.
Definitely. You have traditional programming for straightforward stuff, sequential logic, simple data, but then you have OSP for these highly connected dynamic relational structures.
And the OSP advantage seems to be that natural graph representation, the automatic traversal with walkers, and that type-driven interaction you mentioned.
Yeah, it leads to code that's often much more concise, declarative, and potentially scalable for problems where the connections between data points are just as important, if not more important, than the data points themselves.
I still have that nagging question, though. Why not just use a Python library like NetworkX? It's popular, it handles graphs.
It's a fair question. But when you use a library, the graph is still fundamentally just, well, data sitting in memory that your Python code manipulates from the outside.
Okay.
In Jack, the graph structure, the nodes, the edges, and the traversal logic in walkers, they are understood natively by the compiler and runtime. It's not just a data structure, it's part of the execution model itself.
So potential for deeper optimizations, maybe even parallelism.
That's the promise. Because the structure and the computations movement are inherent, the system can potentially optimize traversal, distribute work, manage concurrency in ways that are much harder to retrofit onto a general-purpose language using just a library. It's about building the graph into the execution fabric.
So thinking bigger picture, AI, knowledge graphs, recommendation systems, complex simulations, what's the real takeaway here?
I think it comes back to that OSP mantra. Don't bring data to computation. Send computation to where the data lives. It's a fundamental shift.
A different perspective on system design.
Totally. Instead of pulling massive amounts of related data into one central place to process it, you design these lightweight intelligent agents, the walkers, and you send them out to explore the structure, perform tasks locally, and report back what they find.
It feels more distributed, maybe more biological in a way.
You could say that. So the final thought for you, the listener, is this. Think about the complex, interconnected problems you face or see in the world. Logistics, social dynamics, biological pathways, maybe even code dependencies. Could sending computation out to the data, letting it walk the structure, be a more effective way to find the answers you need? Which graph are you going to send a walker into?